Okay, everybody, we're going to be doing a lab in which we are going to be placing some hydrochloric acid into a petri dish, and so that's what I'm going to go ahead and do. This is 1 molar hydrochloric acid in the petri dish, and I'm going to go ahead and add to it 0.070 grams of the magnesium that I'm doing. So I have hydrochloric acid reacting with magnesium, and it's going to make magnesium chloride, as you know, and some hydrogen gas. And so that means that when we do all of this, we are going to be creating a gas, and as a result, the gas is going to produce a mass change because we're letting the gas be released into the air. So what we're going to see is a mass change as a result. So my initial mass is going to be the mass that we see that is the highest mass right at the moment that I add the magnesium to it, and I'm going to click start at the same time. So my initial mass is 18.506. So at time 0, my mass was 18.506 grams. And I'm going to be recording the mass every 30 seconds. So at time 30 seconds is the next time we're going to record. And at time 30 seconds, our mass is 18.488. 18.488 grams. At time 60 seconds, that's our next one. Now give it a thought here. When I'm recording these, you're seeing an overall decrease in mass, and so it's the gas that is being released that is causing that decrease in mass. So we are getting ready to record time 60 seconds, which will be 18.466. 18.466 grams. And then at time 90 seconds, and I'm going to go ahead and pause my video and collect the rest of the data and come back to you with all of the masses. Okay, so we have some data for this first run, and I'm going to move my camera so that you can see it. As you know already, we had the data for 0 through 120, so this is the rest of the data for 0 through 180 seconds. I'll let you get that recorded. And then we have the data for 210 through 390 seconds. That is an 18.343 right there, everybody. And then our final two data points were these two right here, 420 for 18.226 and 450 for 18.215. Okay, our last reaction was with 0.070 grams of magnesium and with 20 milliliters of 1 molar hydrochloric acid. We are still going to use 20 milliliters of 1 mole hydrochloric acid, and that is what I just put in the petri dish. But now we are going to add to that the 0.070 grams of shredded up or pieces of magnesium instead of a ribbon of magnesium. And we are going to go ahead and get I'm trying to get that on the screen so you can see it. I'm going to go ahead and get my timer started as well. So we are going to record the highest mass that we get once we put this in. We're expecting it to be somewhere around 19.205 is what I'm expecting. 19.207 is what we got to start with. All right, and we needed to start our timer. 19.207 was what we started with. 19.207 was at time 0. And so at time, so that's 0. At time 30 seconds, we're going to record our next. And as you might be able to tell just by looking at it, it does seem to be bubbling more vigorously this time. It is going down. So our time at 30 seconds is 19.170. 19.170. That's our grams at 30 seconds. So we're going for 60 seconds next. And we're almost there. 19.140. 19.140 at time 60 seconds. And I'm going to go ahead and pause it and collect the rest of the data. Okay, and once we got done with the data collection on this next part, we got the rest of the data. We stopped at 60 seconds, so you see it ranged down to 180 seconds there. And so then we also completed with the data for 210. Let me see if I can get it all on here, and I'll go ahead and pan to it. 210 for 210 through 330, and then we ended at 450 on this one at a total lowered mass to 18.873 grams. Okay, so that was a comparison between large pieces and small granulated pieces. Okay, so our next one, as you can imagine, is now going to be where we change the temperature. Okay, so for this one we are using hydrochloric acid, 1 molar hydrochloric acid, but it has had its temperature increased by 10 degrees. And we need to remake this to 0. And I've got to pour that back in. You guys, the struggles are so real. Okay, so this empty mass is, there it is, it's zeroed out. So the mass with our 1 molar warmed up hydrochloric acid is 19.653, to which we're going to add 0.070 grams of magnesium. So I'm expecting the high to be 19.6715. Okay, yep, that's what it came out to. 19.713 is where we came out to, and I am starting the timer right now so you can, there it is, so you can see it. And so our first one was 19.715 grams. That was at time 0. So our next one is going to be at time 30, and we are coming up on it right now, and it's going to be at 19.662. 19.662 grams. And then at 60, and we're almost there, 60 seconds, we're going to record that as 19 point, almost ready, 607. 19.607, and I'll go ahead and record the rest of the data after I pause this so that you can get all the data. Okay, so our data looks like this. We made it to 180 seconds and 19.437 for the first column, and then for the second column we made it all the way to 330 seconds, 19.403 grams all the way. Our final result was 19.320 grams. And so make sure you go ahead and record your data. I think that kind of shows us all the data right there. All right, our last example of rates of reaction is going to be where we change the molarity. In this last example, our molarity is going to be 2 molar. Everything else will remain the same, including surface area and temperature. Okay, for this one I am going to be using 20 milliliters of 2 molar hydrochloric acid, so that is going to be our change that we are making, and we are going to add to that the exact amount of 0.070 grams of magnesium. I am going to go ahead and set this up so that it can start. I need to go ahead and make sure we can see and I need to turn this around because it is backwards. There we go. And let me go ahead and make that be so we can see it. So I need it like that. You guys, the struggle is real here. Okay, our timing. I am going to go ahead and add, if we're adding 0.070 grams to 20.60 2 grams, then we're going to have 20.670 grams. So here we go. And we did end up with 20.67, and I'm going to go ahead and start our timer. So our starting grams was 20.670 grams, and that was at time 0. And so our first reading at 30 seconds is going to be at, almost there, 30. There we go, 20.576 grams, and I will continue taking the data until we get this one already finished up. So our final readings for the last trial, where we doubled the concentration of the hydrochloric acid, came out like this. All right, so what we need to do now, after you've got a chance to write down all of your data, is we need to talk about, well, what does this look like when we have to figure out how much gas is being evolved each time. So each time you are going to have a value that you started with, 20.670 grams, and then you're going to have, that's a 7 there, everybody, you're going to subtract what value you had at a certain time. So at 30 seconds, we had remaining 20.576 grams. So, and you know that the uncertainty for each one is plus or minus 0.001. So when we are subtracting, we're going to add those uncertainties together with each other. So doing this subtraction, and yes, I need my calculator to do this subtraction because my brain is not going to work. Doing this subtraction, if I could find a calculator, I'd be really, really happy. There it is. 20.67 minus 20.576. And so I have this particular first amount of gas release was 0.094 grams plus or minus 0.002 grams. And so that's an absolute grams value. So that's the kind of calculation you're going to need to place. So for 30 seconds, in the first 30 seconds, we lost 0.094 grams. You're going to need to repeat that as an overall amount, a cumulative amount. So your next subtraction is going to be 20.670 minus 20.516 grams, and you're going to continue that way. And so that is the first thing that you need to do for your lab. Okay, so for how to make your amount of your graph, let's go ahead and talk about this. You can find this information on page 163 of your book. And this gives a really good idea of the how the graph should be set up. It's going to be set up as volume of, in this case, H2 that is formed versus time. So our first volume that was at time 30 seconds, so we would have a volume plotted, and it's going to start looking a lot like this kind of shape of a graph. Remember, please, that when we are doing these, we also have to be able to calculate the slope of the line tangent to the graph. So we're going to draw a line that is adjacent or tangent to the graph, and we're going to calculate the slope of that line. And it's those 4 slopes that we are going to compare with each other when we are asking the question. And so ultimately we have the things that you need to do. Number 1 are find the volumes of gases at each temperature, or at each time, per time. All right? Then with the graph, once you get the graph, you are going to need to find the slope of the line tangent to the graph for each graph. Okay? And it is going to be the comparison of those slopes that is going to give us which set of conditions is going to produce the greatest change in rate of reaction. And we want to know, in this comparison, I'd like you to write about it, which produced the steepest slope, therefore which is the one that most greatly increased the rate of reaction. I think I can guess already what it's going to be. You might already be able to guess what it's going to be. I expect there to be a graph that is fully labeled. In other words, your graph will have time in seconds with a plus or minus. In this case, it's plus or minus 1 second because we were using a digital device. And we are also going to have a unit label for the volume. So that was our x-axis. Our unit label for our volume of H2 gas is going to be with a plus or minus uncertainty of 0.002. Remember, we had to subtract. And the unit label for this is going to be grams, because we were collecting it in grams. So it's going to be, in fact, it's going to have to not be volume. I take it back. It's going to have to be grams, or mass of gas evolved. Okay? So you're going to do your calculation to calculate your gas at each time. Then you're going to graph it with grams of H2 on the x-axis and time on the y-axis. Whoops, I said it oppositely. Hold on. All right, let's say that again. On the x-axis should be time. On the y-axis should be grams of H2. You're going to determine a slope of the line tangent to each curve so that you can compare the slopes and those initial rates of reaction. Remember, we're looking for initial rates of reaction. So you're going to be using a line tangent to the beginning of the curve. All right, good luck, everybody.